Today we are going to discuss an innovative model called Flibs'NLogo, which is implemented in the NetLogo modeling environment. This model uses a genetic algorithm to evolve a perfect predictor from a pool of digital creatures known as Flibs. These Flibs or finite living blobs act as agents that attempt to predict change in their environment through their interactions. So, before our chat, can you please introduce yourself?
Yes, my name is Cosimo Leuci, and I teach at an adult school in the southeast of Italy. My educational background is in biology, and during my postgraduate training, I have engaged in research that concentrates on the genetic and molecular responses of cells to diverse environmental stresses. Currently, my interests are centered around the study of complex adaptive systems with some theoretical aspects that relate to both my post-research and my current teaching activities. In pursuing these studies, I'm using an agent-based modeling approach, and Flibs'NLogo was one of the first model I developed.
To start off, can you explain the purpose of your model and what motivated you to develop this?
I had a different motivation for developing the model. The first one was simply to see it run. As a student, I had written an early version in basic language after reading about it in an issue of Scientific American magazine. But my Commodore VIC-20 did not have enough memory to operate it. Many years after, I revisited the model in an agent-based framework, believing it could serve as a foundation for exploring topics I find compelling, such as how organisms respond to environmental challenges. I also find very exciting the possibility that this concept intersects with epistemological inquiries about the growth of knowledge. I have to say that I'm not a professional programmer, and I remember that one of my initial challenges was transitioning from procedural languages to agent-oriented language like NetLogo. This shift brought many technical challenges, but basically I think improved my programming skills. The journey was also educational in various other aspects. For instance, it was quite amusing to observe myself and to see how new ideas for solution can emerge. Sometimes they pop up suddenly in the mind, while other times they require studying handbooks or the code of other modelers. I can remember one of the earliest challenges I encountered, which involved coding the crossover process. The Flibs'NLogo model make use of a genetic algorithm in which genome shuffling is essential. To validate the accuracy of this subroutine, I created a simplified model. And as a biologist, this experience was interesting because it allowed me to glance at the difficulties that nature may have encountered during the evolution of sexual reproduction. But I also mentioned that occasionally something may be overlooked. With the Flibs'NLogo, I'm grateful to the anonymous peer reviewer for identifying a bug in the code of which was unaware. The model first insight was to illustrate a possible way in which an external reality can be integrated into a cognitive entity. From my point of view, this idea echoes the concept of the structural coupling introduced by Chilean theorists Maturana and Varela. And it was fascinating for me to observe how it could arise simply through probabilistic processes such as Darwinian selection. Now, I will not try to explain how this may happen, but the program is freely downloadable together with the attached documentation, and of course I am available to provide further information about the model. It could also be an opportunity for me to get feedback on my work.
I think you already explained the challenges of the model, yes?
Yes.
Thank you. So, moving on the results, what are the main insights coming out of the model analysis and how do they contribute to our understanding of genetic algorithms?
It was just a preliminary work because as can explain, this program was the basis for a further application. Flibs'NLogo tackles a well-defined problem, but in the history of life on Earth, as well as in our everyday life, we often encounter ill-defined problems. I'm building on the work started with Flibs'NLogo by adapting its architecture to the Alfaro bar problem, which is a kind of problem without an ultimate solution. The first version is available on ComSysNet as well, and I am currently developing an enhanced version in order to expand its capabilities. I'm also interested in studying how genomes or cognitive systems reassemble when they encounter unfamiliar situations. In this context, I have already uploaded the Hypermoon model, and I plan to integrate as soon as possible these two lines of exploration into a single model.
So, you've made your model available using ComSys platform. So, can you tell us about the challenges you faced in the process of archiving your model via this platform, and what steps did you take? I mean, to address these challenges.
I'd like to begin by saying that I'm confident that agent-based modeling is a powerful instrument for the study of complex phenomena. And its impact for science could be similar to the introduction of instruments such as telescopes or differential equations in classical physics. On the other hand, open science should be regarded as a common good, including its impact on peer review, result reproducibility, and the free exchange of ideas. So the main challenge I faced in making my model accessible through ComSysNet was writing a clear and concise documentation that details the model's peculiarities in a way that is easy to understand and reproduce. However, I have to say that in the case of Flibs'NLogo, the task is made easier by referring back to the original article by Alexander Dewdney, which I read years ago and still consider an excellent reference point.
Finally, looking ahead, what's next with this topic, and are there follow-up studies available or planned to expand on your current work?
No, the model will be built in the usual part of a genetic algorithm. The central part, the main part, and three different, at least three different subroutine. Mm-hmm. The fitness function, reproductive function and mutation function. These three parts can be more or less complicated, but the skeleton of the program will be always the same.
Mm-hmm. So thank you for sharing your insights on this model with us.
Thank you for your interview.